Okay, so maybe we can get started. Welcome back. So first of all, I think a lot of you are looking for the chapter notes for today's lecture. I tried really hard until 3 a.m., but I couldn't finish it, so I did not put it. Okay, so there was an important conference deadline yesterday, and several of my students were submitting for the conference, and like this was a really busy week. So I should have written this note probably a week earlier, but I couldn't. I have partial notes, but today is going to be a real live lecture, like uh, with with half of the course, like with half of the lecture with no notes. Okay, so but I hope it will be all right. But I'll be releasing the notes in a few days. Like so, like it's halfway through. Like once I finish it, I'll release it. And next week is a break, right? So I should be able to finish the future notes and release that as well. Okay, so before we get started, like second assignment was released last week. So, and immediately several students complained in the anonymous feedback form that the assignment is long without even trying one question in the assignment. Okay, so I think the problem is just the description. Like so, it looks like a 5-page assignment. So it looks like it is very long. Okay, it is not long. So has anyone read the assignment completely, like before giving that feedback? Okay, has anyone in the class read the assignment A2? You have read it, right? Like so.
It's not that long.
It is not that long. If you read the assignment, maybe it takes the initial effort. Okay, so the immediate reward is less because like you have to read 5 pages. But once you read it, you will know that it's really simple assignment. So you only have to write one algorithm, and you will just modify that algorithm for all the questions. Okay, so you implement a Monte Carlo, like update it to TD, all the questions follow. Like so, it is a simple algorithm. Like it is a simple assignment. It's not a difficult assignment. The reason why it is long is just to make sure there is no ambiguities. Okay, so the first assignment was brief, and there were a lot of ambiguities. Like if you go read the assignments, you will appreciate that TAs have clarified as many things as they could. Like for example, even for plotting, they have given the plotting function. For environment, they have implemented the environment and give it to you. Like so, like you just need to run your algorithm with the environment. Okay, so like I should appreciate the TAs have put a lot of effort for the second assignment based on your feedback for the first assignment, so which is good. So hopefully we will do even better third assignment. But given that everyone is feeling assignments are always long, I'll try to do a shorter third assignment. Okay, so that you don't think all the assignments are long, but the second assignment is really not long. I highly encourage you to start reading it and implement things, and it should be really easy. Okay, so maybe let us get started. Okay, so given that there are no lecture notes, like, but I'm sure there are only few of you who read the notes before class. Anyways, like, but you have to follow more closely today because there are no notes available yet. Okay, okay. So where did we stop last week? Anyone? What did we saw last week? So what did we see last week? People remotely can just type your answers in chat, like I will read it. Okay, so but there's a very general answer. So what did we cover last week? Temporal difference learning, right? Like so. Now to quickly summarize, like different things that we have covered so far, right? Like in this course, like so, like we are mostly looking at algorithms to solve the reinforcement learning problem, right? Like so, well, first of all, we post reinforcement learning problem as an MDP, and then the problem becomes solving the MTP to find the optimal policy, right? Like so, like the first approach, which is not really a learning approach that we have seen, is like the idea of dynamic programming, right? So in dynamic programming, like you assume that the model of the world is given to you, then you just do value iteration or policy iteration to find the optimal policy. And so it's It's efficient if you have them access. If you have access to the dynamics function of the world, it is useless if you don't have that, right? Like so. Then we talked about Monte Carlo methods, I guess, which is basically like a learning based approach where you are learning the value functions, okay, by just sample averages over the experience, right? So the advantage of Monte Carlo over dynamic programming is like it doesn't require access to the model of the world, and you can learn from experience or through interaction, right? Like, and it is just sample averaging. It's easy to compute. And but one problem with Monte Carlo is like it expects you to finish the episode so that you can compute the sample returns, right? Like now, this is problematic if you have really long episodes, and it is also not possible if you are in continuing task when there is no end, right? Like so, in these kind of situations, like so, we can use temporal difference learning, which is what we discussed last week, right? So TD, instead of waiting for the entire episode to terminate, just waits for one step to terminate, like one step to finish, and then you already compute your target updates based on the reward and the value of the next state, right? It's kind of a bootstrapping approach like DP, except for the fact that it doesn't require model of the world. It's like sample update instead of expected update that you're doing in DP, right? So, and we also, I think towards the end, we also discussed that we can actually kind of get the best of both Monte Carlo and TD by using n-step TD methods, right? So where n is a hyperparameter, like you have to try different n, and it's a hyperparameter in the sense like there is a sweet spot, like so maybe n is equal to 2 or n is equal to 4 or 8, like but there's a sweet spot for every problem, and like so that is going to help you to get the best of both worlds, like Monte Carlo and TD, right? So this is where we stopped, and towards the end of the lecture, I did mention that we will take a pause in like coming up with new solutions for reinforcement learning and focus on some of the other problems that we would face when we want to use these algorithms in real life, okay? So today's lecture is going to be about value function approximation. Okay. So far, if you think about how we implement our algorithms, okay, so they are all tabular methods. Okay, so I'm going to call them as tabular methods because you can implement all these algorithms that we have seen so far, like value iteration or policy iteration, or like constant step Monte Carlo or whatever, or like Q-learning or Sarsa, right? Like so, all the algorithms that we have seen so far, you can implement it by using a table, like which has number of rows equal to the number of states, right? Like you have this vector which is capturing the values of the states, and we always assume that we can actually enumerate the states, right? Like so, for example, in the grid world assignment that you did, like so there were 25 states, which means you have a 25 size vector or a table, like where you just update values, continue this forever, and you're going to converge, right? Like so these are all tabular methods. Like they work fine, like when you have simple problems, like the grid world that you have seen. Okay, now what happens when you have like large scale problems? Like so imagine like you want to like maybe we can go back to the same backgammon example that we see once in a while, right? Like so if you think about the game of backgammon, there are like 10 power 20 states approximately. Okay, now first of all, we cannot store 10 power 20 states. Okay, now this is not just the issue of memory. Even if you can store the values of 10 power 20 states, you cannot learn them in limited time or finite amount of time. Okay, so when the number of states increases, like when you're in extremely large state space, okay, which is the common situation that you will see in several real world applications, okay, so then you need more memory to store these tables, but memory is not the only issue. Like you also need like significant time and data to learn these tables, okay. Now like another example that I could give is like playing Atari. Like so, like well, I think we never saw like Atari video in this course. Like so, probably we'll do it next week, next to next week, like when we talk about deep reinforcement learning. But I'm sure like a lot of you would have played like simple games like Pong or Breakout, right? Like so when you play such games, like so imagine you have to design a reinforcement learning agent to like play those games. Like now the states are really what frames of the video that you are seeing. So now there are many frames that you would see, like so, and like the state space here is so huge that if you attempt to do a tabular approach like we have done so far, you are not going to succeed. Okay, now it is not just because the states are large. Okay, there is also a second reason why these methods will not succeed, which is basically in most of the interesting problems you will not see the same state again. Okay, so states rarely repeat. Okay, so for imagine like you're playing like a very complex video game which has several rooms and like levels. Okay, now the states are your observations, like so whatever you're seeing in your TV. Now you can think that you can imagine that as you progress in the game, you're going to see new and new states, right? Like, and this is going to continue forever, and you will not see the same state again. Like you might see some of these states again, like, but most often like you will see new and new states. And now the reinforcement learning problem is a bit different. Like the problem is not about just mapping from states to action, but it is more about mapping from unseen states to action. Like so you care about doing well in situations you have not seen at all. So you have not learned to act in this new situation, and you have to act here, right? Like so now this idea that you should generalize to unseen states, like learn, like you should generalize your policy to unseen states, right? Like so this is known as generalization. Okay, so if you are in the ML course, like, or if you have taken an ML course before, then you know that machine learning is all about generalization, right? Like so in the classical machine learning, like when you do supervised learning, like we care a lot about generalization. Like we have a separate training data where we train our model on, and then we also have a separate test data there, like we test the generalization capabilities of these models. Okay, however in reinforcement learning, like when I say generalization, this is a little bit different. It's different in the sense I care about generalizing to unseen states in the same game or in the same task. Okay, now imagine you have learned values of a bunch of states. I give you a new state. Can you estimate the value of this state, like with very high accuracy, right? So now this is important because if you can do that, then you can actually construct a policy to act in this totally unseen state, right? So that is the kind of generalization that we care about. Okay, now how to achieve such generalization, right? Like so now there are yeah.
Basically, we only try to estimate for a particular number of states, and any new state we always try to see if it's similar to one of these states and take a policy based on that.
Okay, you are talking about a solution now.
No, I'm just asking if the approximation.
Oh yeah. Well, no, but still, like you're giving a solution, right? Like so, your solution is if you see a new state, see which old state it is very similar to, and then you try to approximate the value using that.
So there are still more number of solutions.
Yes. So that is one way to solve this problem. Okay. So we will see many solutions today. But in general, like to summarize, like there are two reasons. Okay. So how we are going to do this generalization is through function approximation. Okay. So now if you think about classical supervised learning setting, okay, so if you think about classical supervised learning setting, like so, like there has been a lot of work in designing function approximation models, like where you have a bunch of xy. Okay, and the goal is to learn a function f, which will take input x and make some prediction y, such that given a completely new X, your prediction Y is going to be as accurate as possible. Okay. Now, to give you an example, let's say you are interested in predicting stock price. Okay. Now, in this case, like you will have a bunch of inputs. Like the X is going to be a lot of features about the particular stock that you care about. Okay. And Y is basically the price of the stock. Now, you see thousands of examples of the features and the corresponding stock price. And given a new data point, like can you predict the stock price as accurately as possible, right? So now this is one example of a supervised learning task where you can design a simple regression model, like which takes input X and tries to make some prediction Y, right? Like, and you can design as complex model as you want, right? Like, so for example, like there are linear models, which are basically some linear, like where Y is a linear function of X, okay? And you can even have nonlinear models, like neural networks, where your Y is a nonlinear function of X, which means there is more expressive power that you can model highly complex functions, okay? Now this is quick intro to supervised learning, right? Like, so now how can I borrow ideas from supervised learning to our topic or problem of focus, which is the idea of estimating values, right? So if we go back to our discussion on reinforcement learning, so our goal here is to estimate value functions as accurately as possible, right? Like, so I care about the value functions. Like once I get the value functions, then I can compute the policy, right? Now, in large scale problems, like we discussed two issues, like which would be a problem in estimating these value functions. Like, so what was the first issue? The first issue was, I think, yeah. So the first issue was there are large state spaces. And the second issue is need for generalization to unseen states, unseen future states. Okay. Now how do I use ideas from supervised learning to estimate value functions? Okay. So any ideas?
You can use the value functions and then the corresponding actions that you took and try to generate with.
Okay, so we are still not talking about actions here. Okay, so we are just estimating the value functions. We are not estimating the policy here. Anyone? Yeah.
Learn a function approximator between the value and the states, and then try to use that.
Okay, so the suggestion is to learn some function approximator, which will try to predict the value of a state. Okay, so you can have some function approximator, okay, which takes input state as the input, okay, and predict v pi of s. Now the next question is like, how do I train this function approximator, right? So that is what we are going to see in today's lecture. But the general idea is you train it through the experiences that you have, okay? So now if you think about it, like, so you can take Monte Carlo or PD. In most of these approaches, like you have some target update, right? Now you can treat your target updates as the prediction of this function approximator. Now, when you experience in like episodes, like in the real world, like you're going to collect these experience and you're going to treat this as your data set for training this function approximator. Okay. So, however, there are some differences in like supervised learning and between supervised learning and this function approximation for value estimation. Okay, so there are like the first major difference is that like in the case of value function approximation, we care a lot about methods that learn incrementally from acquired data. Okay, so learning incrementally, okay, is important when compared to this. Like in the case of supervised learning, like for example, let's say you're doing image classification, you will have a data set which is fixed, right? Like some 1,000 examples or 10,000 examples, and you go through this data set again and again, like to learn like a function which maps images to classes, right? So on the other hand, like with reinforcement learning, the agent is also collecting the data on the fly, right? Like so you interact and you get some data and you use that for learning the function approximator, and then you interact more, you get more data, and you use this for function approximator and so on. Okay, so this is one fundamental difference. So the second fundamental difference is in the case of linear, like value function approximation, right? So we should be able to handle non-stationary target functions. Okay. So this is again completely different from supervised learning, because in supervised learning, your target is very clear. Like given an image, you have to predict whether this is a dog or cat, and the training data will tell this is a dog. Okay. Your target is never going to change. But in the case of value function approximation, your target might change for several reasons. Okay, so can somebody tell me like why your target would change here? Like there are many reasons why targets would change.
So the policy and the changes.
The policy is changing, right? Like so when the policy changes, target changes. Like any other reason? Let's say we are okay. Maybe this is a quiz. So that's the right answer. Like when the policy changes, your target changes. Now let's say I'm doing prediction. Okay, given a policy, I'm estimating the value function. So there's only one policy. Even then, there could be non-stationarity in the targets. Yeah.
And you don't know the value function to begin with, so you'll be using some approximation to start with, and that will change.
Yeah. So for example, if you're using methods like TD, right? So what is the target in TD? Anybody? So what is the target in one-step TD?
Is it reward plus the value function of the next?
Yeah, so reward plus gamma times value function of the next state, right? Like so, now who gives you the value function of the next state? You are estimating it as well, right? Like so now this is a classical bootstrapping issue, right? Like so you can take DP, or you can take TD, or you can take even n-step TD. In all these algorithms, like you have this component in the update which is actually dependent on the value function that you're estimating. Okay, now as you learn better and better, this part is going to change. Okay, so let's take TD for example. Like so in TD, your update, your target is basically RT plus 1 plus gamma times value of state T plus 1, right? Now, you don't have access to this, so you're estimating this as well. As this estimate changes, your target value actually change, right? Like so this is very different from supervised learning. In supervised learning, like your target doesn't change, but here your target changes. So we really need methods which can handle this kind of non-stationarity, which is a key characteristics of reinforcement learning. Is that clear? Okay, so I think, so now we have set our goal. So our goal is to come up with some function approximator which takes a state and try to estimate the value. And this is going to do this for whatever states and values that we have experienced so far. And the goal is to use this function approximator in the future when we see a completely unseen state. Is that clear? Any questions so far? Okay, there are some right answers in the chat as well. Any questions so far? Okay, so I think for this lecture and the next lecture, okay, so we will talk about different function approximators, like starting from very simple linear models today, all the way to very complex deep neural networks. Okay, so but first let's start with simple models. Okay, so we're going to do value function approximation. but first with linear models. Okay. Now, our goal is to estimate v pi of s, okay, which is my value function. Okay. But what we are going to do here, instead of having a table to estimate this, is to have a parametric model which is going to fit this value function. Okay. So we are going to call our approximator as v of state given some weights w. Okay. Now this is an approximation to v pi of s. Okay. So this is an approximation. Now, this approximator has some weights w. Okay, so let's say w is some d-dimensional vector. Okay, so the idea here is to have a small function approximator to approximate an extremely large table of functions. Okay, so a table of value functions. So generally, so this d, the dimensionality of this function approximator is going to be much lesser than the number of states that you have. Okay, so I haven't told you yet what is v, right? So v is some function which takes a state as input and it has its own parameters w, okay, and it computes an estimate of the value function like by using both the given state and this w. Okay, now there are many ways in which you can construct this v. This v could be a linear model, this v could be a neural network, this v could be a decision forest, or it could be a simple decision tree. You can use any function approximator that you have seen in machine learning to approximate this v, like to approximate this value function. Okay, but to begin with, let's have a very simple linear model. Okay, so now for each state yes, consider that we have constructed a bunch of features. Okay, and we are going to call these features as x of s. So x of s is basically a bunch of features okay, which represents the state. Okay, now this is the representation of the state. Okay, now so far we did not care about how the states are represented, right? Like, so we were always, even in your assignments when you implemented these algorithms, like you would have just indexed states as state 1, state 2, state 3, state 4, and so on, right? Like, so now we are going to talk about representing states in an efficient way. Okay, so what do we mean by representation of a state? Like, so for example, let's say we are designing an agent for driving cars. Okay, so in the case of self-driving cars, like the state of this agent is basically whatever it sees, right? Like, so now I could have one feature which records the speed of the car. There might be one feature which says whether there are pedestrians in the road or not. There might be another feature which says whether the signal is on or off. There might be another feature which is dark, like a bunch of other things. Okay, so basically any useful information in the state that you can encode, you're going to encode it as features of the state. Okay, so then your representation of the state is basically this collection of features. Now these features are numerical values so that it is easy for us to use mathematical models. Okay, so like for example, like if you care about whether the signal is red or green or yellow, right? So you could have one feature which is 0 for red, 1 for green, 2 for yellow, and so on. Okay, so you take all the information that you want, you encode it into these numerical features. Okay, so that is what the state representation is. Now this is a place where you can really put all your domain knowledge. Like when you construct the representation for the state, if you construct a really good representation which captures the essence of the observation, then it is going to be easier for the RL algorithm to learn the value function. Okay, if you have really bad state representation, then estimating the values from this bad state representation might be very hard. Okay, so this is one place where you put your domain knowledge. Okay, so and you have we're going to talk about how to construct these features probably in the second part of the lecture. But for this part, let us assume that we have the state features. Okay, now given any problem, let's say somebody give you the state features as well. Now the model is really simple. Like my model V of S given W is going to be simply W transpose X of S. Okay, or in other words, summation over I is equal to 1 to D Wi Xi of S. Is that clear? Now, I want to highlight how different is this thing from our previous ways of solving this problem, which was a tabular method where you would just have the state and its value. So state 1, state 2, state 3, state, let's say there are 100 states, okay, state 100, and the corresponding values, right? Now, the learning problem in this value function approximation is to find the W, like find the right W such that like your predictions of values are as accurate as possible. Okay, so now there are okay, philosophically there are quite a few differences between these two approaches. Okay, let's take time to understand that. Now, in the case of tabular approaches that we have seen so far, okay, there is no interaction between the learning of different states, right? So I can learn the estimate for S1. It is actually independent of the estimate for S2, right? Well, if you're using bootstrapping, then there is some dependency, but for the moment, let's take Monte Carlo. Okay, let's just talk about Monte Carlo, okay? If you're doing Monte Carlo estimates, then there is no dependency between the value estimates of these states, right? Like they're decoupled and you're learning them separately, okay? But if you're doing Monte Carlo estimates with this kind of function approximation, okay, so then you can see that it is no more independent, like the value estimates are no more independent, because let's say for state 1, I make some modifications to W so that the estimate is good for state 1, okay? Now the same W is used for all the states, right? Which means if I modify W to get better estimate for state 1, it is going to affect all the other states' estimates. Now, this is a balancing problem. Like I want to find the right set of W such that I get low error in estimating the value of all my states. And we did not have this balancing problem here. Like here it was very simple in the sense you have 100 states, you learn 100 estimates separately, there is no interaction. Is that clear? Is that clear? Okay, so now this, yeah?
So in this case, I just understood a doubt, maybe it might be wrong. So I think for each state we'll have different value functions because we are taking from different iterations, right? In that case, how does it approximate? Like,
Each,
the question.
okay, what's the question? Each
so we'll be taking the value functions from different steps, right? So for a single state, you will have different value functions.
Yeah, oh, we talked about that, right? Like, so the question is, if we are updating the value, like W based on like the target from different iterations or episodes, then the value of the state is going to change, right? Like, so we talked about that. That is the issue of non-stationarity. Like, so the what is the right estimate for the like what is the target for your value estimate is going to change as the episode progresses.
But how does it learn? Because for a single state, it might have different values. How will the model?
We will talk about it. Okay, we will talk about it. Okay, but do you get the fundamental difference between the approaches that we have seen so far and this idea of function approximation? Now, you might think this is a problem, okay, but this is actually not a problem. Well, it is a problem, but if you solve this problem of balancing, like such that you find a W which works for all the states, it has a huge advantage. So the advantage is when you are learning about one state, you are indirectly learning about all the states. right? So like you can actually learn to generalize if you have a function approximator, and you cannot learn to generalize like with tabular approaches. With tabular approaches, okay, no generalization. Okay, like for example, let's say there are 100 states in the world. You do Monte Carlo, you never visit 99th state. Okay, now Monte Carlo, tabular Monte Carlo will tell you that the value of this 99th state is whatever you initialize it to, like let's say 0. Okay. However, if you do function approximation plus Monte Carlo, right? So we're going to see how to do that like very soon. But if you are doing function approximation with Monte Carlo, then even if you have not seen state 99, if you see that for the first time, you will actually have a better estimate because the state representations help you to generalize. Is that clear?
Isn't that because here we are learning to understand what are the features in a state more than the state itself?
No, that is not true. So the point is, okay, so his comment is we are learning to understand the state. No,
Features in the state.
features in the state. No, we are still not doing that. Okay, so we will do that next week. So we are still not learning to understand the features of a state. Like features are given to us. Okay, so somebody gives me these features about the state, and I am just learning the value function.
So you're learning how the features are connected.
Yes.
For a state.
So we are just learning a mapping from the features to the value function. Yeah.
If you are learning approximation with Monte Carlo, is there still non-stationarity?
With Monte Carlo.
Or that your targets are stationary? I mean, I don't know how it's.
Oh, your policy, well, if you're doing prediction with Monte Carlo, there is no non-stationarity. But if you're learning, if you're doing control with Monte Carlo, then your policy is, the policy that you're trying to estimate is constantly changing, right?
Yeah, no, policy will just keep it.
Oh, if you keep the policy fixed, then Monte Carlo has no non-stationarity. Okay, so I think like I convinced you that it's a good idea to do function approximation, even though it is a hard method, right? Like so. Now let's talk about how to do that in detail. Like so first we will see how to move from tabular to this kind of function approximation methods. Okay. Now, as I mentioned before, like so you can kind of have a template for all the algorithms that we have seen so far. Okay. So we will see how to extend all of them to the idea of function approximation. Now, all the algorithms can be written in this way. Okay, so you have some state and you have some target update for the state. Okay, so this is the state and this is my target update. Okay, so for example, let's say we are doing Monte Carlo. Okay, in the case of Monte Carlo, for every state ST, can someone tell me what was the target update in Monte Carlo? GT, right? So you are kind of trying to move your estimates towards GT. Now, similarly, in the case of one-step TD, for every state, what was the target update?
RT plus gamma.
RT plus 1 plus gamma times V of ST plus 1. Now, in this case, we are in the function approximation case. Like so, the value is actually estimated from my function. Okay, and we have n-step TD. So in the case of n-step TD, like our estimate was basically, our target update was basically GT to T plus N, right? Where the idea is you are following the return until T plus N, and then you are approximating the rest by using the value function, okay? And we can also bring DP here. So in the case of DP, for every state, the target update was basically this whole expectation term, right? So expectation with respect to policy, RT plus 1 plus gamma times V of ST plus 1, given ST is equal to S, right? Now, in all these algorithms, right, So you take one update. Now you can consider that update as an example. Okay, so the example is basically, like for example, in the case of Monte Carlo, my example is going to be st comma gt. Okay, similarly in the case of one-step TD, my example is going to be st comma, like whatever the target update is. Okay, now in the case of tabular approaches, if you think about how we implemented Monte Carlo, like so we will already have an estimate for the state. We will move that. So we will move that a fraction of amount towards this GT, right? Like by using the alpha, right? Similarly for TD, this is the estimate, but we will not directly go there. Like we will do some alpha times the estimate, so that like we are taking a fraction step, right? So however, and that was only affecting that particular state, right? However, in the case of function approximation, when you are updating W, and this W update is going to affect all the other states, right? So now there is a trade-off here, right? Like so, like you by construction of this function approximation, like we decided to go with smaller number of parameters such that D is D is much smaller than the number of states, right? So which means this function approximator does not have enough power to represent the table accurately. Okay, well, if you can represent the, also our goal was not to do that, right? Like so, then we can go for the tabular approach. So we want a good approximation for the table, right? So which means we need some function approximator which does well, like as much as it can for every state, right? Now, the first realization here is like we cannot accurately estimate the value of all the states. So then the next question is, are there any important states where we should have very high accuracy in prediction? And like for other states, like you might have less accuracy, right? Like so, now this is the practical trade-off that we will often make in a lot of reinforcement learning algorithms. So if you think about it, like going back to the backgammon example, I told you that there are 10 power 20 states in backgammon, okay? Or maybe there are like similar number of states in chess, okay? So let's say chess has 10 power 30 states, okay? I may be wrong. Now, in reality, you will never see these 10 power 30 states, okay? You will not see all possible configurations of chessboards. Like you will only see a very tiny fraction of possible configurations of the chessboard, okay? Which means it's kind of unnecessary to aim for a function approximator, which is going to have very high like accuracy in predicting the value of these states that I will never see, right? I only care about states that I will actually see in my experience. So imagine I have this distribution of states. Okay, so we're going to call that as mu of S. Okay, so if I have this distribution of states like that, I will be, where the distribution is in such a way that mu of S is greater than or equal to 0. The probability of the state is greater than or equal to 0. And it sums to 1, so that it's a value probability distribution, okay? So imagine this distribution represents how much we care about a state, okay? Then the objective for function approximation, I can write a new objective for function approximation, okay? So the prediction objective, okay, we are going to call this as VE bar, okay? So VE bar of W is given by summation over S belonging to S, mu of X, V pi of S minus V hat S comma W the whole square. Okay. Now, so this is my objective for function approximation. Okay. So this is a typical mean squared error. So if you have seen regression before, like, so what we are really trying to do in value function approximation is regression, right? Like, so we are trying to regress the value of the state. So mean square error is like a normal error or objective that you would use for such cases. Yeah, I think maybe.
Can you just repeat what mu is?
Okay, I will talk about mu. Your question? Okay. I haven't explained what is mu, right? So mu is some distribution which tells me how much I care about one state. Okay, so here is the thing. Okay, maybe it's easier if I write it in a different way. Okay, so now let us just, okay, so what would be the objective for this value function approximator, right? Like so we want to learn W. Okay, now if you want to learn W, like you need some objective so that, okay, this is going to be really hard for me. So maybe let me quickly take a vote. How many of you have done a machine learning course or in my machine learning course currently, like both? Okay, so I don't need to, okay, is there anybody who has not seen any supervised learning? Even if you've done an AA course, you would have seen supervised learning. So, because I'm kind of rephrasing things so for people who don't know machine learning. Also in people in Zoom, like, is there anyone who has not seen it's okay to say yes, like, so that I will be explaining things in a different way. So is there anyone who has not seen supervised learning at all? Okay, so then I don't need to pretend that you don't know supervised learning, okay? So now, so this is a regression problem, right? Like, so we are interested in finding the values of W, which such that like the value, like we have very good prediction, like estimate of the value function, right? So now, what would be the objective of this function approximator, right? Like, so we need some objective, like, so in this case, this is a regression problem. So the obvious objective is mean squared error, right? So now, one way to think about it is like you consider all the states that you have, okay? So summation over all possible states, okay? The true value of the state minus the model's prediction. Okay, you can add 1/2 if you want. Like you can also divide it by s, like if you want an average. Okay, it doesn't matter. Now this is what we care about, right? Like, so we are interested in finding a function approximator which will have, so the goal is to find W star, which is basically arg min of V of E, right? So this is what our goal is. So what I discussed just 5 minutes before is, this is kind of an unreasonable goal. It's an unreasonable goal because I really don't care about all possible states in this task, okay? I only care about a fraction of states which I will ever encounter, okay? Suppose somebody gives me this fraction. Suppose somebody tells me out of this 100 states, these 10 are the most important states, okay? Then I can construct a probability distribution over the state, which tells the importance of the state, okay? That is what my mu of s is, okay? Based on the mu of s, I can adapt or update, modify this VE to something like this, okay? So this is my modified objective. My modified objective is summation over s belonging to capital S, okay? Mu of x multiplied by v pi of s minus v hat of sw the whole square, okay? So all I'm doing here is I'm giving weight for each state. Like for example, if there are states that I don't care about, I can set mu of those states to 0. So then I'm not penalizing my model, like my function approximator, for not accurately predicting those states. You're helping your function approximator by saying, oh, don't focus on these states because they are not important, and focus on these states because they are very important. Question?
What is x? It's supposed to be s, right?
Okay, yes, yes.
Same on the previous page.
Okay, so yeah, that is true. So S is basically S of x. Okay, any questions?
But what will be very difficult to get the mu of x, because
Yes, that is a very good question. So who is going to give us this mu of x?
So is it like?
I know we have to stop for break. Should I leave that as a question or? Okay, let's leave it as a question for the break. So this is what I want to do. Okay, but the like an appropriate question here is like, who is going to give me the mu? So what is mu? Okay, so of course nobody's going to give us mu for really complex problems, right? Like, so then what is a good approximation for mu? So think about it.
Based on your.
Think about it, and like we will talk about it at 10:30. So we will continue at 10:30. So